Welcome to the IMSAI channel, where I try to resurrect an old IMSAI 8080 computer. Okay, I thought I'd document what I did to get the IMSAI talking, in case somebody wanted to duplicate it. We can start here. This is the circuit that connects to the speaker. Let me zoom in on that. So pin 1 connects to the SSI-263 chip. It goes through a low-pass filter, 4.7K resistors and 0.1 microfarad capacitors. So it's a double filter into a 10K resistor. So this is the volume pot. I use a LM386 chip for the amplifier. Pin 3 connects to the pot, 2 goes to ground. 5 is the output through a 10 microfarad capacitor to the speaker. I'm using a 4 ohm speaker, but I think anything works just fine. There's some extra pins on the LM36, 386. Pin 4 is ground. Pin 6 goes to +5. You could tie that to +8 in the system, or even, I'm not sure if this chip will take 16, but certainly it takes +8 if you want to get a little more power out of the speaker, a little more volume out of the speaker. There's 10 microfarad between pin 4 and 5, between pin 4 and 8. 4 and 8, pin 5 is the output. And then another filter on pin 7 to help some ripple rejection, 0.1 microfarad to ground. Alright, so let's look at the bus then. This we've seen before. This was my Centronics interface. S input and data bus in are ANDed together, so those both have to be true. And the not match, which checks the high order bits of the address lines. All of those three have to match before it gives a data in enable. That's the signal that's used to actually read the handshake flag back from the SSI. Then there's another signal that's basically the same thing, only on output. The output and the not right are ANDed together, and they're also ANDed together with the not match to give a not data strobe. That's not used in this design, but the unused portion of the LS00 NAND gate was used to invert this and give a data out enable. That was used as CS0, pin 19 on the SSI chip. The other chip select 1, which is inverted, that was tied to ground. The read not write was also tied to ground, so this is only writing to the SSI chip. So that's how that was done. And let me find page 2. And make sure you can read this. This is a little bit smaller. Let's just start up here. So this is the data lines in to the part, and in order to create a handshake that happened right in the center of the data, instead of trying to gate these, I just left them tied to +5 volts. So these data lines are always inputting to the chip, and they go to pins 9, 10, 11, 13, 14, 15, 16, 17 of the SSI chip. On the output of the SSI, pin 4 is used as a open collector handshake. There's a 1.7K resistor to +5 volts. It's tied to pin 7, so 0 through 7, so it's the high order bit, and that goes out to the data bus. This tri-state buffer is being driven. This is being driven by the not data enable, which was oh, is that true? I don't think it's inverted. I think it's actually a high state. So it's this signal being used, the data out enable. I don't remember now. It's one or the other. Check the data sheet. Maybe it is. I think maybe it is the not data strobe that's being used on. I'm sorry, this is the input section. Forget me. It's this signal here, not data in. It is a low true, and it's the signal. This is not used. This is used into pin 19, and this is used, and it's used here on data in enable. I'm sorry about that. All right, and then this is the matching circuit that takes a look at the high-ordered address lines to make this card address at E00. So the switches are set for E. Since we're using A0, A1, and A2, this chip was also using the A2. And so right here is a cut. So this is not being input to this chip any longer, and I grounded pin 11. This switch should always be closed for a ground. And then these are set, like I said, for address E0. When this is true, when address E0 actually appears on the data bus, then this signal goes low, the not match signal goes low, and that notch match signal comes to here for this handshake. That card has a 5-volt regulator on it. And then there's a couple other signals that are wired directly to the S100 bus, and they go directly to the SSI chip. One being not reset, which is pin 75 of the S100 bus. I'm not sure if that was needed or not. It's nice if it gets hung into some strange state where it's just making some lousy noise. When you hit the reset button, it immediately quiets the chip. So it's a nice feature to have. So pin 75 goes to pin 18 on the SSR chip. And then the RS0, RS1, and RS2, which are pins 8, 7, and 6, those are the ones I had reversed, 8, 7, and 6, go to pins 79, 80, and 81 of the S100 bus. That's an 81. And that's A0, A1, and A2. They get connected directly to the bus. And then pin 49 is a 2 megahertz clock that appears on the S100 bus, and that is directly connected to pin 22, which is clock on the SSI chip. And this is a div2, divided by 2. That is pulled high on pin 23. That tells the SSI chip that you have a 2 megahertz clock coming in and divide it down. It wants a 1 megahertz clock. So if you happen to bring in a 1 megahertz clock, ground this pin. If you bring in a 2 megahertz clock, then tie it high. And that's it. So if you're going to build one of these, it's pretty simple. Just make sure you wire it right. That was one of my big problems. Make sure your board is working correctly. The board was kind of old, but we got it working. And the only other hard part is trying to find an SSI-263 chip.